Hello, 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 hello. Hi. Hi. Very excited to have a special guest here today. John Rauser is a data scientist at Pinterest and formerly a principal engineer at Amazon. I've seen him give talks at Velocity and Strata, fascinating talks about looking at your data and doing really interesting investigations on data. He's also done some really fascinating work on looking at performance data and what can be found there. And his personal mission statement, which I just heard, is to help people think more clearly. So anyway, help me welcome John Rauser. Thanks very much.
All right, so this talk runs about 55 minutes, so I'm going to be super on the rails in an effort to get you out of here on time. So I'm John Rauser. I am a data scientist at Pinterest, formerly of Amazon, and I'm here to talk to you today about TCP and the lower bound of web application performance. So this is a play in 3 acts with a short prologue and a short epilogue. The big picture is that it's a talk about how the web works and why it works that way. And so I mean that in 2 different ways. First, it's a talk about how the web works because I spend the bulk of the talk explaining in some detail one of the fundamental low-level communication protocols of the internet and how that protocol puts a lower bound on web application performance. But it's also a talk about how the web works because I'm going to talk a lot about how the internet was created and how it's governed. Okay, so away we go. We begin in 1996 when this guy, Stuart Cheshire, wrote a famous paper called "It's the Latency Stupid." This paper starts with 2 observations, the first of which is that making more bandwidth is easy. So imagine that the only network line that you could get at your house was a 56K dial-up line, and you had an application that needed more bandwidth than that. Hey, that's no problem, because you can just get another phone line and tie the 2 together, and now you have double the bandwidth. If you needed even more, you could get like 10 or 20 lines, tie all those together with some kind of crazy networking equipment, and now you'd have something approximating like a DSL line. It would be expensive and it would be annoying, but you can do it. You can make more bandwidth. But Stuart's second observation is that latency is different from bandwidth. He says once you have bad latency, you're stuck with it. To see why that's true, maybe we'll look at an example. Let's say that you live in Seattle and you want to start a website, and there's this super awesome hosting company on the East Coast. And so you set up an account with them, and you set up your new site. And now to talk to your new site, your messages have to go 3,700 kilometers in one direction, and the responses have to go 3,700 kilometers back for a total of 7,400 kilometers. And the question is, how long does that take to make that round trip? And so think about that for a second right now. Don't shout out the answer if you know the answer, but come up with a guess. What is the round trip network latency from coast to coast? So to answer that question, first we'll look at the science. The speed of light in a vacuum is about 300,000 kilometers per second. It must be true because Google says so. So to traverse 7,400 kilometers at 300,000 kilometers per second takes about 25 milliseconds in a vacuum. But your signals aren't propagating in a vacuum. They're propagating in glass in the form of fiber optic cables. And the index of refraction of glass is 1.5, which means that light travels in fiber at only 66% of the speed at which it does in a vacuum. And so the theoretical limit on round-trip latency, it's not 25 milliseconds. It's more like 37 milliseconds for a signal to go from coast to coast and back in a single, unbroken piece of theoretical fiber with no networking devices in the way. And so if this is the theoretical minimum, how long does it actually take? Well, from my house in Seattle when I lived there over a Comcast cable modem with consumer-grade networking equipment, it takes about 90 milliseconds. So we should think about that for a second. So remember, the theoretical round-trip latency in fiber was 37 milliseconds. We're only about a factor of 2 away from that. And the thing is, it's been like this for over a decade. Cheshire did this analysis in 1996 between Lawrence Berkeley Labs and MIT, and he got essentially the same result, about a factor of 2. So networking devices are pretty darn good already, but they are not getting any faster. And so truly, once you've got bad latency, you're stuck with it. So this is fascinating. I hear you saying to yourselves, remind me again why I care about any of this. So Stuart Cheshire cared about network latency because in 1987, he wrote one of the first real-time multiplayer internet games. And in gaming, 100 milliseconds is the difference between an experience that feels crisp and an experience that feels sluggish. But you all should care because you're in the business of making web applications, and it turns out that network latency matters for web applications. To understand why network latency matters for web applications, we need to understand how the internet works. To understand digital networks, the internet's a digital network, it helps to contrast them with another kind of a network, an analog network. So if you go all the way back to the dawn of telegraphy in the 1800s, the earliest electronic communication networks were what are called circuit-switched networks. With a telegraph, there's a single pair of wires, a circuit, connecting the keys at either end. When telephones were invented, it was the same thing. In the early days of telephone networks, there were rooms full of humans who would plug wires into switchboards to make a physical connection, a circuit, between you and the person you wanted to talk to. And that circuit would then be dedicated to your conversation. So if the operator pulled the plug, you would be literally disconnected. That's why we still use that word when we talk in terms of connections in digital networks. Be literally disconnected from the person on the other end. Then later on, we developed these beautifully engineered electromechanical switchboards. This device is called a crossbar switch. You can see that there are 10 screws across the top and then 10 more at the bottom where you can connect wires. So there are 100 possible ways to connect the top to the bottom. The machinery in the middle can arrange itself so that simultaneously it can make any 6 of those 100 connections. Crossbar switches like these can then be ganged together into something called a CLO network. And with CLO networks combining large numbers of 20 by 20 crossbar switches, you can build a worldwide telecommunications network with millions of subscribers. And up until fairly recently, this is how the phone system worked. You could pick up a phone anywhere on the planet, dial the number of somebody on the opposite side of the planet, and dozens of little machines between you and them would physically rearrange themselves so that there was a continuous circuit between the two of you. And that circuit would be dedicated to your conversation for as long as you cared to talk. And so you can see why long-distance calling used to be so expensive. So that's an analog, a circuit switch network. But with the advent of digital computers, people realized that you could send messages much more efficiently if they were digital messages. With a digital message, you don't need to dedicate a given circuit to a single conversation. You can easily break a digital message up into chunks called packets, and then you can send each packet through the network separately, and then reassemble them back into the complete message on the other side. And so if you're communicating with analog signals, people have historically used circuit switch networks, while with digital signals, you can use a packet switch network. And once you change to a packet switch network, you get enormous efficiency gains because you can send many conversations simultaneously over the same network link. To be concrete, here's like the simplest possible network diagram. There are 2 sites, one at the top, one at the bottom. Each site has 3 hosts connected to a router, and there's a single long-haul circuit connecting the 2 sites. And so with a circuit switch network, only one person at the top can talk to any one person at the bottom all at the same time. But with a packet switch network, everybody can talk to everybody else simultaneously because their messages are broken into packets and interleaved over that single long-haul connection. But there is a problem. There's no free lunch because all the possible connections are uncoordinated. If everyone talks all at the same time, they can overwhelm the available bandwidth on that single connection. To make that concrete, so imagine a phone line. If 2 people are having a single conversation, everything is fine. But if many people are talking simultaneously, they end up talking over each other, right? You've had this experience on a conference call, no doubt. The more people there are, the bigger the chance of collision. And so packet switched networks make more efficient use of the available bandwidth, but they need some way to fairly deal with congestion. Dealing with this problem is one of the fundamental research areas in computer networking, and the main point of this talk is to explore the congestion control mechanisms of the modern internet. But before we get to that, I need to lay a little bit more groundwork. I want to talk about the origins of the internet and how all of the disparate networks that make up the internet come to agreement on how to communicate. So recall our simple network diagram. In the 1960s, there were already primitive networks, primitive packet-switched networks that looked pretty much like this. In 1965, there was a network connecting the Advanced Research Projects Agency, or ARPA, in the US Department of Defense, with the Systems Development Corporation, or SDC, in Santa Monica. In the 1960s, ARPA funded all kinds of basic computer science research, and they used interactive computers with primitive forms of email to communicate with the remote sites. ARPA also supported the Multics project at MIT and the Genie project at UC Berkeley. And the networks actually looked like this. Each of these systems had been developed locally. They all used different hardware and custom networking protocols. And so there were offices at ARPA with 3 different terminals, one for each of these networks. And you couldn't use the MIT terminal to talk to the people at UCB. You had to physically get up from your desk, walk over to the UCB terminal, sit down, log in order to talk to the folks at UCB. And so we had computer networks in 1965, but what we didn't have was an internet, a network of networks. And then in 1965, the head of the Information Processing Techniques Office at ARPA, a fellow by the name of Robert Taylor, was sitting in one of these rooms with 3 terminals, and he was struck with an idea. In a 1999 interview with John Markoff, he recalls saying to himself, "Oh man, it's obvious what you do. If you have these 3 terminals, there ought to be 1 terminal that goes anywhere you want to go with interactive computing." That idea is the ARPANET, which is the precursor of the modern internet. In 1966, Robert Taylor went to the head of ARPA with this idea, and he got funded immediately. Taylor said that the head of ARPA, a fellow by the name of Charlie Hertzfeld, liked the idea so much that he took $1 million out of the ballistic missile defense budget, and he put it straight into Taylor's budget, right? And if that is not an enlightened government funding decision, I don't know what is. Right? Like, less missiles, more internet, thank you. So by 1968, Taylor had developed a complete plan for a computer network. There's the internet in 1968. The first 4 sites would be UC Santa Barbara, UCLA, the Stanford Research Institute, and the University of Utah. Again, he went and he got funding from ARPA and a company by the name of Bolt, Beranek, and Newman, or BBN, very important company in the history of the internet. They won the contract to build out the initial network. So if you were a computer scientist, this was an incredibly exciting time. At this point, it was clear that the basic infrastructure of a global computer network, a capital I internet, was going to get built, but it was not at all obvious what anyone was going to do with it. Specifically, BBN had been contracted to build out the long-haul infrastructure that would get messages from site to site, but the software that was supposed to run on the host, the local hosts, that was left to the sites themselves. And so in August of 1968, a handful of graduate students and staff members from the original 4 internet sites began meeting intermittently in person, because there was no internet email, to try to figure out how the host software for the internet should work. In the spring of 1969, they had whittled themselves down to a working group of 3 people, and they decided that they should start publishing the results of their discussions. And it was Steve Crocker who volunteered to write up their notes. And when you think about the task that he had signed up for, it's really sort of frightening. The ARPANET had not yet been built, but it was clear to everyone involved that it was going to be a big deal. And here's Steve Crocker. He's a lowly graduate student, right? He's just a grad student. And he and a few other folks were speccing out the host software for a multi-million-dollar government project to build the world's first global computer network. And so as he was getting ready to publish the group's notes, he became increasingly nervous. He worried about sounding presumptuous. He didn't want to sound like he was making any sort of official decision or asserting any kind of authority. Looking back on this time 30 years later, he wrote, "Mindful that our group was junior, informal, and unchartered, I wanted to emphasize that these notes were the beginning of a dialogue." Extremely important word in the history of the internet, a dialogue, and not an assertion of control. And so he named the series of memos Request for Comments. Very humble, right? It's just a request for comments, that's all it is. This is Request for Comments, or RFC number 1, host software. It's actually still really fun to read all these years later because they got a lot of it right, but it's somewhere between comical and painful to see them struggle with issues like escaping binary data, right? Like nothing has changed in 40 years. So this document is where the dialogue that is the internet begins. The RFCs document the technical discussions of internet protocols. Some RFCs have special status as standards that the internet community as a whole has agreed to. And in some conceptual sense, the RFCs are the internet. The RFCs are the technical specifications of the internet, and the way that you change the internet is you publish an RFC and get people to agree to adopt it. And so the RFC process is how the internet adapts to a changing environment. And the next part of my talk tells one story of how the internet adapted when cracks started to appear in its foundations. Okay, so now the stage is set, and we're ready to start with the big action. We pick up the story again in September of 1981 when the modern internet was born. In September of 1981, this guy, John Postel, published RFC 793 documenting for the first time the Transmission Control Protocol, or TCP, in the form that we know it today. The TCP algorithm provides for 6 basic properties, but for the purposes of this talk, we only care about 2 of them, reliability and flow control. First, we'll look at reliability. Here's the text from RFC 793. It says that reliability is achieved by requiring positive acknowledgement from the receiver. To see how that works, we'll look at an example of the simplest possible transaction. Here's the canonical client-server sequence diagram, right? Time flows down and messages flow back and forth. So the client sends some sort of a request. In this case, it looks like it's an HTTP GET verb. The server sends its response. The client acknowledges the receipt of the response. And now the client has the data. The server knows that the client has the data, and all is well. I'd like to point out that each of these arrows in this diagram is a packet, right? TCP is a digital communication protocol that works over packet switch networks. And packets get dropped all the time on the internet. So what happens if a packet is lost or damaged during transmission? Hey, no problem. The server sets a timer when it sends each packet. And if the timer goes off, it then retransmits the response. So now the client can acknowledge, and we're in the same state that we were before. The client has the data, the server knows the client has the data, and everybody is happy. So we see how acknowledgements provide for reliability. What about flow control? First, what is flow control and why do I want it? Networking devices have limited buffers, and when those buffers fill up, the inbound packets, they just get dropped on the floor. So to ensure that the buffers don't fill up, the receiver needs a way to control the flow of data, to limit how much data the sender could put on the wire at any given time. Here's what the RFC says about flow control. It says that flow control is achieved by returning a window with every acknowledgement. Here's the important part. The window indicates an allowed number of octets, that's bytes if you're a network engineer, an allowed number of octets that the sender may transmit before receiving further permission. Or saying it a different way, the window size is the amount of unacknowledged data that can be in transit at any given time. To understand how the window provides for flow control, we'll look at another example. Let's say that during connection negotiation, a topic which I will not talk about in any detail at all, somehow, magically, during connection negotiation, a client advertises a 5 kilobyte window and a maximum segment size of 1 kilobyte. What the heck is a maximum segment size? I haven't said what that is yet. The maximum segment size is the largest amount of data that the network can transmit in a single packet. If any packet is larger than this, it has to be broken apart and then reassembled at the other end. Fragmentation and reassembly is expensive, so we seek to avoid it. So basically, the sender promises, I'll always send packets smaller than that maximum. So as before, the client sends a request. Let's say that the response is 10 kilobytes of data, so it has to be broken up into 10 1 kilobyte packets. And since the window is only 5 kilobytes, we can only send 5 of them at first. And then the client acknowledges each packet as it processes it, and the server receives each of those acknowledgements. And as it receives each of those acknowledgements, it can put one more packet out on the wire, keeping the window full. And as before, the client acknowledges each of those packets. The ACKs land on the server, ACK, 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 ACK. And now we've sent all 10 packets. They've all been acknowledged, and we're all done. It's just like before. The client's got the data. The server knows the client's got the data. Everybody is happy. And that is TCP in September of 1981 at the birth of the modern internet. And at this time, there were 213 named hosts on the ARPANET. In May of 1982, there were still only 235 named hosts. But it's at about this time that a bunch of things happened. First, Sun Microsystems was founded in 1982, and not just Sun, but a bunch of companies started to release powerful workstations that were based on 32-bit architectures like the Motorola 68000. And then, in 1983, BSD 4.2 was released. BSD 4.2 is important because it contained the first widely deployed implementation of Postel's TCP/IP, really surf and cons TCP/IP, but the version of it published by Postel. So software and hardware collided to create explosive growth in the number of nodes on the internet. This is the number of nodes on the net over a 10-year span from 1981 to 1991. Here's the same data plotted on a log scale. So if you do a little bit of arithmetic, you can see that it starts doubling every 9 months starting in 1982. And things were going great until about 1986, when the number of hosts on the internet had grown to about 5,000, so a 25-fold increase since Postel had published RFC 793. And it's at this time that the cracks started to appear. In October of 1986, the internet had the first of what became a series of congestion collapse events. And in retrospect, it's not too hard to see what the problem was. TCP's window size, this window I've talked about, it's allocated 16 bits in the header of a TCP packet. And so the maximum window size is 64K. And so if a client requests a large file, the server might jam 64 kilobytes of data down the pipe all at once. And at this time, the internet was a series of little sippy straws, right? Little wide area sippy straws connecting large, like 10 megabit Ethernets. The original NSFnet links were 56 kilobit lines. And also remember that you got to walk Moore's Law back 30 years. Memory was much more expensive in 1986, so internet gateways had much smaller buffers. And when a gateway runs out of buffer, it drops packets. And when packets get dropped, they need to be retransmitted. This retransmit timer that I talked about earlier, it's dynamic. The TCP stack is constantly measuring the round-trip latency of the connection, and it adjusts the retransmit timer accordingly. But when something like this happens, it can shock that measurement system, and round-trip times can jump up so quickly that the measurement algorithm lags behind. And when that happens, you're in big trouble. So John Nagel was one of the first people to document this problem. In 1984, he wrote RFC 896, which describes the problem so well, I'll just read you a couple of passages. First, he notes that a sudden load on the net can cause round-trip times to rise faster than the measurement algorithms can be updated. If this happens and the round-trip times exceed the maximum retransmission interval on any host, then that host will begin to introduce more and more copies of the same datagram into the net. The network, he notes, is now in serious trouble. Eventually, all available buffers in the switching nodes will be full and packets will have to be retransmitted. Hosts will be sending each packet several times, and eventually some copy of each packet arrives at its destination. This is what we call congestion collapse. And this little phrase here is a critical point. It turns out that TCP is extremely persistent in trying to deliver packets. And just due to chance, some of the packets actually get through, and that keeps the connections alive. And this is important because it implies a terrible result, which is that the condition of congestion collapse is stable. Once the saturation point has been reached, Nagel says, if the algorithm for dropping packets is fair, the network will get stuck in congestion collapse. And so Nagel wrote all this up in 1984, and he cheerfully noted at the time that congestion collapse is not normally seen on the ARPANET because these systems have substantial excess capacity. Right? Well, remember, that was 1984, doubling every 9 months. Here's the Usenet posting from 1986. Nancy Cassidy in mod.risks talks about the critical congestion problems of the internet. Mail messages. She's talking about email messages taking 2 to 3 days to be delivered, right? Like, if you're like me and Gmail like takes more than about like a half a second, right? I'm spamming that refresh button. Right? So 2 to 3 days is pretty ridiculous. Enter Van Jacobson, the fellow widely credited with saving the internet from collapse due to traffic in the late 1980s. Like any good scientist, what does Jacobson do? He sets up an experiment. He had 4 machines on a 10 megabit Ethernet at Lawrence Berkeley Labs, each send a 1 megabyte file to another 4 machines at UC Berkeley. And the trouble is that even though these Ethernets were just 400 meters apart, they were connected with a 230 kilobit microwave link. So any pair of machines could overflow the available buffer on the interconnect, and all 4 of the machines talking together could exceed the available bandwidth by 160%. And so what did Jacobson see? It wasn't pretty. So this is a trace from Jacobson's paper. Each point on this trace is a packet. On the x-axis is the time the packet was sent, and on the y-axis is the sequence number of the packet. So a vertical line of dots represents a set of packets all sent at the same time, and the dotted line that comes out of the origin, the dotted diagonal line, that shows the available bandwidth of the interconnect between the two Ethernets. So things look pretty good at first, right? We jam 40 packets into the pipe, and everything's going great, except, oh, this packet gets dropped and has to be retransmitted. And then this packet gets dropped to the internet, and it has to be retransmitted. And then we're off to the races again, but, oh, there's another dropped packet, and then another one, and then another one, and it gets better. This packet gets transmitted not once, not twice, not 3 times, not 4 times, but 5 times. So to quote Jacobson, nothing in this trace resembles desirable behavior. So at this point, Jacobson had seen the behavior at the root of the internet's congestion problems. And in response, he crafts what we know today as the TCP slow start algorithm. So we've already talked about this window that is maintained by the receiver, which provides for flow control. But that is not enough, Jacobson observes, and so he introduces another window known as the congestion window, which is maintained by the sender. And before, when I said that the window was the maximum amount of unacknowledged data that was allowed to be in flight, well, now it's the minimum of the regular window and the congestion window that put a limit on how much data the sender can shove down the pipe. The congestion window is controlled by 4 very delicately intertwined algorithms, and the precise nature of these algorithms is actually an area of ongoing research. There have been many proposed algorithms with all kinds of goofy code names like Reno and Vegas and New Reno. There's something called Vino, which is a combination of Vegas and Reno. Modern Linux kernels use an algorithm called binary increase congestion control, or BIC, or actually even more recently something called cubic. Microsoft with Vista, they completely rewrote their TCP stack. They use something called compound TCP. So there is an enormous amount of variety out there. But what I'm going to describe first is what's documented in RFC 2851 and 3390. And the good news for my talk is that slow start, the one piece that I'm going to talk about in detail, that hasn't changed a whole lot since the late 1980s. So here's how slow start works. First, the sender initializes the congestion window to some number of full-size segments. Until recently, that number was 3 segments. And then every time the sender gets an acknowledgement, it increases, every time the sender gets an acknowledgement, it increases the congestion window by 1. And this results in the congestion window opening exponentially. So we'll look at an example of how that works. As before, the client sends a request, but now if the congestion window starts at 3, the server can only send 3 packets of the response. The client acknowledges those 3 packets, and for each ACK, the server increases the congestion window by 1, and so now the congestion window is 6. So the server can send 6 segments. The client acknowledges each of those, making the congestion window 12, and by now you can see that the congestion window opens exponentially. It doubles with every round trip. This is what's known as the TCP slow start algorithm, and it turned this into this, which is much nicer. So in June of 1988, an implementation of TCP slow start was released on the world in BSD 4.3, and in November of 1988, Jacobson and Carrolls documented this work in a paper called Congestion Avoidance and Control. It's a beautiful, very readable paper, which I recommend you look up. There's a link at the bottom. Slow start was codified as an internet standard in 1988 with RFC 1122. Here's the text from 1122. It cites Jacobson's work, and it says a TCP must implement this algorithm, and every TCP stack ever since has. And now we've arrived at Act 3. Finally, the culmination of my thesis is at hand. 147 slides and 27 minutes later. TCP slow start means that network latency strictly limits the throughput of fresh connections. After RFC 3390, in the first round trip, you can only get 3 packets. It doesn't matter if you have infinite bandwidth. TCP slow start says you're only getting 3. Hey, no problem, you say, I'll just send really, really big packets. It doesn't work that way. Modern Ethernet limits you to packets of 1,500 bytes. You take away 40 bytes for the TCP and IP headers, and you're left with 1,460 bytes. And so in one round trip with an initial congestion window of 3, you can get a maximum of 4,380 bytes. Hey, no problem, you say, because I'm running a web service of some variety, and I'm operating over HTTP. I have HTTP 1.1 persistent connections, and slow start only affects the first hit. And that actually might be true, but it's worth recalling Yahoo's slightly long in the tooth research from 2007, though I think still relevant, where they found that 1 hit in 5 was from a browser with an empty cache, right? So at least 1 hit in 5 was a first hit for Yahoo in 2007. I have no idea what it's like for you cats at Etsy, but I'd bet that a lot of your hits are first hits. More generally, if you know that your average session length is n and you make some assumptions that are here in the fine print, you can guess that your fraction of hits is, your fraction of first hits, pardon me, is 1 over your average session length. In short, it is difficult to escape this problem. No problem, you say. I have a further objection. It's only 5 round trips until the window's fully open. And you'd like that to be true. The Windows field is 16 bits wide, I said. 2 to the 16th is 64K, divided by maximum segment size of 1460, and you get that a maximum window size is 44 segments. And if the congestion window doubles in size with every round trip, it's only 5 round trips before you're shipping a full window. Except maybe not, because of the delayed ACK algorithm. So what's the delayed ACK algorithm? The delayed ACK algorithm was introduced in with RFC 813 in July of 1982. This is what the RFC says. Basically, this business of ACKing every packet the instant you get it, that's excessive and it's wasteful. To see why that's true, we'll look at another example. Let's say you're running an SSH session and you're going to change directories. So you type the C of your CD, and that gets fired off to the server because you're in character mode. The server can acknowledge instantly. This is something I've glossed over so far, but both sides of the connection send acknowledgments. So far, I've only been showing the acknowledgments on the client side, but both sides send acknowledgments. So before the server, the server acknowledges, but immediately afterward, the server needs to echo back the character that you just typed, right? The echo that shows up, or the C that shows up on your screen, it's not the C you type, it's the C the server echoes back. So the server echoes, and the client acknowledges the echo instantly, and now you type the D of your CD, and the whole dance starts again. The server acts, the server echoes, the client acts the echo, and now you've typed 2 characters. We've sent 8 packets. Every one of those 8 packets contains 40 bytes of TCP and IP overhead. So this is wasteful. The delayed ACK algorithm says, don't ACK right away. Wait for 100 or 200 milliseconds. It's configurable, but maybe there'll be some data to send in a little bit. And what we can do is we can piggyback the acknowledgement along with the data, because the acknowledgement lives in the header of a TCP packet. So here's what this looks like with the delayed ACK algorithm in place. You type the C, that lands on the server, and the server delays its ACK. It says, well, maybe I'll have some data to send, and sure enough, there is. There's the echo of the C, right? This is all happening at the TCP layer, like way down in the kernel, not at the application layer. So the TCP layer doesn't know what's gonna happen. It just has to wait. And sure enough, some data comes down to the kernel. Please echo this C, and so it can piggyback the acknowledgement of the previous packet along with the echoed C. The client delays its ACK, and then you type your D, and the client can piggyback its ACK along with that D. The server now piggybacks its ACK with the echo of the D, and then there's one final ACK at the end. So this is clearly better than before. We're sending fewer packets and we're using less overhead. Delayed ACK was codified as a standard with RFC 1122, and nearly all TCP stacks implement delayed ACK and have it on by default. It is possible to turn it off. Generally, modern browsers do turn it off, but it's not off universally. Like if you're running like a mobile application, like who knows what's happening in there? I don't know what's going on in your mobile app's TCP stack. It's worth thinking about, this delayed ACK thing. So there's one more thing you need to know about delayed ACK. The algorithm says when a packet arrives, you delay your ACK, but there's one more rule. If another packet arrives while you're waiting, then you can ACK both right away. So since the slow start algorithm updates the congestion window based on ACKs, it interacts with the delayed ACK algorithm. And so for our final example, we'll look at that interaction. As before, the client sends its request. The congestion window starts at 3, so the server can send 3 segments of response. The client doesn't acknowledge the first packet, but it does ACK as soon as the second one arrives. And then there's this funny leftover packet whose ACK is delayed. It's just sitting there like, I don't know, maybe you'll have some more data. The acknowledgement arrives at the server. The congestion window is now incremented to 6, which is great. So now we can have 4 packets out on the wire, but there's the one that's left over from the prior round trip. So we can't send 4, we can only send 3 packets. Now we can finally ACK the one that was left over from the prior round trip, and we can ACK again after 2 more land on the client. Now 2 more ACKs makes the congestion window 6. We can send 6 packets down and get 3 ACKs back, making the congestion window 9. And at this point, you can see that the congestion window isn't doubling every round trip anymore. It's opening more slowly. If you game this out, you see that it takes 9 round trips before you can ship a full window. So to sharpen my thesis, TCP slow start and the delayed ACK algorithm together mean that network latency puts a strict limit on the bandwidth of fresh connections. And we are now in a position to model the absolute minimum time to deliver a web page of a certain size on a fresh connection. If you assume infinite bandwidth and no packet loss and an initial congestion window of 3, if your web page is 3 segments long, you can download it in the first round trip. If you can't fit in 3 segments, there is no benefit to being smaller than 6, which is what you'll get in the second round trip. By the third round trip, you can get 12, and then 21, and then 33, and so on. So what's this mean for a real web page? Here's the Wikipedia page for the White House. The HTML for this page is 291 kilobytes, but we won't have to transmit 291 kilobytes because HTTP supports content compression during transit via the accept encoding header. So the browser only has to download about 61 kilobytes of compressed data, which will fit in 43 1,460 byte segments, which can be transferred in no less than 6 round trips. Now recall that the cross-country round-trip latency on consumer-grade networking equipment is ballpark 90 milliseconds. So for someone across the country, those 6 round trips add up to 540 milliseconds. And if you're on a mobile device, you can easily be looking at well in excess of 200 milliseconds per round trip. And so with an initial congestion window of 3, the fastest many mobile users could get that page is well over a second. And remember, that's with infinite bandwidth and no packet loss, assumptions that are certainly false on a mobile device. Okay, now we come to the epilogue. When I first started trying to understand the effect of TCP on website latency in 2009, this had been the state of the internet for 20 years, since 1989. While I was at Amazon, we experimented with increasing the initial congestion window in an effort to speed up the delivery of web pages. And at first, as we were engaging in this research, I felt a little queasy about messing with TCP in this way, right? RFC 3390 suggests, it's just a suggestion, but it suggests an initial congestion window of 3. And that had been the default for so long that I didn't really know if there were some kind of substantial risk or some sort of hidden downside to starting out with a larger window. Maybe starting with a bigger window would harm some users. If everyone went to a larger congestion window, what would happen? Would the internet fall back into congestion collapse? It turns out that I didn't need to be afraid. At the time that I was working on this at Amazon, there were some other people who were doing the same thing at Google. They were also looking at TCP slow start, and they had conducted large-scale experiments using Google's search front end, testing initial congestion windows as large as 42 segments. And they were allowed to publish their results. And what they found is they got substantial performance improvements with larger windows, but they got diminishing returns after an initial congestion window of 10. They published these results in the ACM Computer Communication Review in June of 2010, but more importantly, they also published an internet draft. An internet draft is a precursor to an RFC, so what Jerry Chu and his colleagues at Google did is to start a dialogue within the internet's governing body about increasing the initial congestion window to 10. And with an initial window of 10, it makes a big difference for the kind of short-lived, medium-sized transfers that dominate the web. This is a plot like the one I showed before. The red line shows the minimum number of round trips to complete a transfer of a certain size with an initial congestion window of 3, and the blue line shows what happens with an initial window of 10. So recall the Wikipedia page for the White House that was 43 segments long and took at least 6 round trips to transmit. Well, if you start with an initial window of 10, and you can have that time to 3 round trips, which is a pretty substantial win for your users. In February of 2011, a patch was merged into the Linux kernel to set the initial congestion window to 10. That change was released in Linux 2638 in March of 2011. And finally, in April of 2013, the IETF published RFC 6928. blessing an initial congestion window of 10 as an experimental change. And this is pretty much the end of the story for now. Most of the internet is currently running with an initial window of 10 with no ill effects. But still, as web pages continue to grow, you've got to wonder whether TCP's congestion control mechanisms will have to be updated further, or whether the web will move to completely different protocols, like Speedy, for example, as it continues to evolve. Okay, so what can we do with this information? It seems like there are a few high-level lessons. The first and most obvious thing to do is to make sure that you are running with an initial window of 10. So like I said, since 2011, the Linux kernel defaults to an initial window of 10. And so if you are running any remotely recent version of Linux on your web servers, you're probably at 10. But there are lots of things that can still go wrong. So lots of sites have caching layers that live in front of their web servers, and that layer can screw up the delivery of the first few packets. What about your load balancers? Your load balancers can screw up what happens in the first round trip. The only way to know for sure is to fire up something like Wireshark or TCP dump and to look at packet by packet traces as a page is delivered, or something like Charles proxy on a mobile device, right? This is the only way to know whether or not you're running with an initial window of 10 or how that first round trip is unfolding. The second thing to do is to carefully consider every byte of content. For HTML, this is probably less important than it was in the recent past. With an initial congestion window of 10, slow start squeezes you much less than it used to. But still, it pays to be aware of the edges that are imposed by the TCP algorithm. You should try to fit in 10 segments or in 25. If you can't get all of your content down in 10 segments, maybe you can get down just enough HTML or just enough JSON or whatever that the user can see some result or can begin interacting with the result in some meaningful way. But again, if you can't fit all of your content in 10 segments, then you should think very carefully about exactly what goes into those first 10 segments. So far, I've completely ignored the size of the HTTP request and response headers, but they eat into the bytes that you can get down in the first round trip. And so every byte you use for your cookies, for example, is one less byte you get for your content in that first round trip. If your page depends on external assets like images or JavaScript or CSS that are downloaded from separate domains or from content delivery networks, it's probably a good idea to get the browser cooking on those connections in that first round trip. And everything I've said about slow start applies to the connections that you use to get those images and JavaScript and whatnot. And so it might be a good idea to think about the order in which you download your images. You might want to start with smaller images that can come down in the first round trip, and then you can have bigger images that you can get in the second round trip, and so on and so forth. And then fourth, just accept the speed of light. Right? Move the client and the server physically closer to each other. This is why content delivery networks exist, and it's why use a CDN was the second of Steve Souders' original 14 rules for faster performing websites. I assume John has given all of you a copy of that book. I don't know, is that true? Probably. If he hasn't, you should ask him for one. Finally, I think that there are a few larger lessons that you can draw from this talk. And the first is that if you're an engineer, there are some parts of the machine that you need to understand, and there are others that you can treat like a black box. And it's different for everybody. If you work at Oracle, you probably need to understand block devices, right? Disk drives incredibly well. If you're doing embedded systems work, maybe you need to understand power consumption or flash memories. But if you deliver an application over the internet and you care at all about performance, then I think TCP is not something that you can treat like a black box. You have to understand how it works in order to be maximally effective. If you're planning to build a business or spend a substantial part of your life working on the web, then you should really understand how the internet is governed. As I said earlier, I said this earlier, but as far as culture goes, dialogue is the fuel that makes the internet go. From the very beginning, the people who built the internet chose an open architecture based on multiple layers of protocol. Here's Steve Crocker, author of the first RFC, reflecting back 20 years later. We were too scared to imagine that we could define an all-inclusive set of protocols that would serve indefinitely. We envisioned a continual process of evolution and addition, and obviously that's what's happened. In the words of David D. Clark, the internet runs on rough consensus and working code. As for formal governance, there's a standards body called the Internet Engineering Task Force, or IETF, that publishes the RFCs. The IETF has written a handy guide for newcomers called the Tao of the IETF. This document lays out the steps that you need to follow if you want to publish an RFC. Basically, the deal in a nutshell is anyone can publish what's known as an internet draft. The bar is incredibly low. That's the precursor to an RFC. From there, you go through a couple of rounds of taking comments and revising your draft. And when you're ready, you convince an area manager to bring your proposal to the Internet Engineering Standards Group, Internet Engineering Steering Group. And then you're on your way to publishing an RFC and possibly changing the internet. The RFC process works as well as it does is completely astonishing, right? Human history is ugly. It is full of war and misery and conflict, and the internet is like some kind of crazy artifact from the optimistic sci-fi future that Gene Roddenberry imagined in Star Trek. In Vint Cerf's words, hiding in the history of the RFCs is the history of human institutions for cooperative work. It's not to be underestimated. And the last lesson is one of humility. Before I started the research that led to this talk, I looked on the people that created the internet as near deities. People like Vint Cerf and John Postel and Van Jacobson and Bill Joy and so many others. And they are certainly some of the greatest engineers ever to walk the face of the planet, but even they didn't get it right on their first try. Their designs cracked under scale, and they had to be repaired over a period of years. And so you should design for the long term. If you're lucky, your ideas might live for 40 years or more. But you should also accept that if your system is successful, it will have to change in ways that you cannot possibly predict. You simply cannot get it all right from the beginning. To take any other position smacks of foolish pride, the kind of pride that the universe finds a way to punish. That's all I have. Thanks for your time. So I can do questions if people want questions. We have like 7 minutes until 2 o'clock.
Yeah, and I have a microphone that I can bring to you. Or remote side.
So can you talk about the the number 10 for the congestion window you mentioned? Is there a theoretical limit on it, or like a way to figure out other than experimenting with this number window?
So that's a good question. I mean, so the question, well, no, you were on a mic, so I don't need to repeat it. Is there a theoretical way to figure out what is the right number? And I mean, I guess yes, but it would only be theoretical, right? Like the internet is this vast amalgam of networks that is completely outside of our control. And so I think Google's approach, which was experimentation, is the right way to go. I mean, I'm hard-pressed to think of something that would be better. That without taking some position, maybe apropos of data, that explained the distribution of latencies, or the distribution of buffer sizes in the switching networks, the distribution of maximum segment sizes. Like you could make assumptions about all those distributions and then crank out a theoretical answer, but I mean, I think that experimentation is really the only way to do it in the real world. I don't know, that's my opinion. That would be a great question for the people that published the internet draft. So if Jerry Chu ever comes, you should ask him. Thanks. More questions?
What are your thoughts on Google's latest experiment, Quick?
Oh my goodness, I don't know anything about it. The question is, what are my thoughts on Quick? I have no idea. I've never heard of it.
They're trying to do HTTP over UDP.
Oh, okay, yeah, this is a common question. Well, there's a common question in this forum. Like basically, can you make a protocol that operates at a lower level or with less promises than TCP gives you? And the answer is yes, you absolutely can. You just have to engineer a new protocol. And if you care about reliability, you have to figure out how you're going to make reliability happen. but you can maybe do that in a different way than the creators of TCP chose to. And maybe you can get some gains for your specific application for medium-sized, short-lived transfers, which is what dominates the web. TCP was designed mostly for large, long-lived connections. That was well, how the internet worked back in the day. And so with different requirements, you might design a different protocol. And apparently Google is doing that, and they're smart people, and so I'm really excited to read about what they come up with.
Remote question. Spike asks, what's the one thing not on Souders 14 that you think we should do?
Oh my word. I can't remember. So the question is, what is one thing on Souders' list of 14 rules that you should do? That's a very good question. Two things come to mind. One is understand that your users come in different classes, that some users are incredibly engaged and have enormous propensity to do whatever it is you want them to do. And you might not be able to affect their behavior, but there's a class of users that are less engaged or who are pressed for time. Maybe they have a 4-year-old tugging on their leg like I do when I'm at home. And those people might be much more receptive to improvements in performance. But those people probably are a much smaller fraction of the population on your service. And so when you do optimizations or you do experimentation, you should try to understand those people and break them out separately, because your effects might be much larger on them. And then the other thing is to experiment, right? Just run tests if you can. It's hard to design tests that measure gains, that measure like business-oriented gains from performance, but you should still try. More questions?
It kind of seems that the way RFCs work to kind of adapt older technologies to newer discoveries and stuff, it kind of seems like it's almost like we're reaching like a local maximum as far as TCP goes. Mm-hmm. Whereas like if potentially instead of like adding new things such as this these windows and whatever, mm-hmm. maybe if you started from somewhere else, you might find a higher maximum. Is there any sort of philosophy behind that? That it's an open question.
It's a good question. Is there a, I mean, maybe your question is, does the IETF tend to optimize incrementally as opposed to looking for, you know, new mountains to climb? I don't have a great sense for that. So I don't actually know the answer to that question. As a practical matter, the IETF is pretty open to all kinds of crazy ideas, right? I mean, so Google published this RFC for Speedy, which is, I mean, I guess it's a pretty far departure, right? I mean, it's a new mountain, a new vista to climb. And I think basically if you can get people to adopt your stuff and start running it, then it's on its way to becoming a standard. I think that the RFC process is extremely open and flexible in that way. That said, I don't have an enormous amount of firsthand experience with it, so I'm really unqualified to answer. Maybe one more question. We have 2 minutes left.
Hi, so we have a lot of people building products here, and we have a huge mobile user base that's growing. What general advice do you have for folks that are starting to think about building their stuff for multiple platforms in terms of performance and what they should be focusing on during the product planning process?
Wow. Okay, very open-ended question. I don't know. I mean, there's two basic approaches, right? Like you can either make the thing work and then make it fast, or you can start out with speed as one of the primary requirements, and design for speed first. And I think you can win with either approach. I mean, I don't know. I'm inclined to say, apropos of nothing except maybe some intuition born of experience, that optimizing for speed first, like having speed as a first class requirement, will get you better results on average, but I don't think that that's necessary. right? I mean, I think if you're trying to design something new and beautiful in terms of UX, and that you might try to figure out how it should work first and then build speed on later. And if you can't build speed on later, then you end up scrapping the thing, and oops, well, that's too bad. But at least you got a shot at something brand new that the world had never seen before. You know, so I mean, that's a super wishy-washy answer, but those are some sort of rough thoughts on the space. Sorry. All right. Thanks for your time, everybody.